Welcome to these web notes on normed vector spaces. And before we get into the heart of the whole theory of normed vector spaces, let's start first by going through some facts and related to the structure of vector spaces. We're not going to be exhaustive, but we're going to just recall some of the concepts that will be useful to us throughout these web notes. If we go to the concept, of course, the keyword here is the concept of vector. So the historical development of the theory of vectors is fairly recent. The old concept is the geometry concept, and we know that if you look at the geometry, which goes back to Euclid and beyond, um, have seen over the years development of this, have seen over the years many new ideas, till of course the main one. I mean, it took off with Descartes when he introduced the concept of analytic geometry, where he introduced a little bit of algebra to study geometry. And one of this of the result of this was that what happened is that R2 is identified with the complex plane. I'm sorry, the real plane, which is a point is given by any point M is given by coordinate x and y. So this is the heart of the analytic geometry. And what happened is we know we cannot add 2 points, okay? But there is a natural addition on R2. So natural extension of the plus, the addition, from R to R2. And this was given by, you can take x comma y, this is plus AB equal x plus A and y plus b. And it enjoys really most of the natural properties of the addition on the real line. For example, the zero element will be 0, 0, etc., etc., without going to and what happened is, what is exactly this addition? I mean, to be honest, what we should do to differentiate between the addition of these pairs of numbers and the natural addition on R is to put maybe a little circle here around it to differentiate it. Of course, if there is no confusion, then we don't put the circle. In other words, to differentiate that this is the addition in R2 versus the addition on the real line. What is the interpretation of this? Okay, so this is the geometric interpretation. So we go to the plane R2. We have the xy and we have AB. And what happened is, if we look at the addition, what is so this is, for example, x, y, a, b, and now we want to look at what is the point x plus a and y plus b. And one way to see it is to consider we draw this one, and then you draw this parallelogram, okay? And what's interesting is that this point here is exactly a plus x and y plus b. So this, of course, reminds us of the parallelogram identity, okay? So this is known as the parallelogram, not identity, I'm sorry, parallelogram law. So this is known as the Newton's parallelogram law. And Newton introduced this to add forces. So he introduced that to add forces. So now this needs a little bit of a little stop and a little discussion here. What happened? We know that the fundamental law of physics of Newton says that the mass times the acceleration is given by is equal to the sum of all the forces acting on the moving object. And here, when he tried to explain, like for example, one of the most interesting problem was the issue of the gravitational force. He knew that this gravitational force cannot be represented, cannot be seen. On the other hand, he can see the action of this gravitational force. So he is the one who somehow initiated the idea of vectors. So you see, a vector cannot be seen, but the action of the vector can be seen. Is this exactly the concept that captures forces is given by the vector. So that was the beginning of vectors. And what you saw here in this paragram law of Newton of how to add this is exactly how to add vectors. So the point here is that people here developed a concept of vectors. So, but before I do that, I need to make a little remark here. Okay? Okay. So let us stay for a second with R2. Okay? And we know that we said that we are now having this operation x plus y plus ab equal to a plus x and y plus b. What happens if I have the same elements, xy and xy? Then according to this addition, it's going to be x plus x, 2x, and y plus y, 2y. And this suggests the following, is that 2 times xy, okay, is equal to 2x to y. So this, in fact, from the addition, we come up with a new operation, okay, which is to multiply each element by a number, okay, given by lambda x, lambda y. So in a very natural way, so we have addition, okay, and now we have multiplication by a number. Okay, natural. One is coming from the other one, so we have these two operations. Okay, of course, one will ask then, what happens if I want to multiply xy with ab, and this is not natural. Okay, there is no natural definition of the product of xy and ab. So again, we have the addition of two elements in R2, and we have a multiplication by a number in a very natural way. So now people offered the concept of vector space. So what is a vector space? So here, so we start first. So here we have the concept of vector space. So what do we have? We have a set V of elements, okay? And the elements of V will be called vectors. So here, of course, this is the general theory or framework offered to capture many examples. We'll see at the end of this introduction some examples that really illustrate how rich is this unified theory that was offered for vector spaces. Keep in mind that for Newton, he was only dealing with forces, and basically they were vectors in R3. Of course, if we have a plane motion, then it's R2, but if we have in a space motion in physics, then we have vectors in R3. In any case, so V will be a set, okay, of elements. These elements will be called vectors, and we need an addition, and we need a multiplication by numbers. Okay, these numbers are called scalars. So when we deal with vector spaces, we have vectors, the element of V, and we have scalars. And these scalars are coming in general, are in a field, K, okay? And usually we'll take K either R or complex numbers C, but it doesn't have to be. It can be like numbers in Z, mode 2, for example. There are many examples of fields that can be considered, and it leads to some very interesting vector spaces. In any case, throughout these web nodes, I will only take throughout these web nodes, I will take K to be R. Great. So, of course, we have one element, special element, that we need to pay attention to. Special element is the zero vector. Okay? So, what's going to be the zero vector? So, sometimes you will see 0 with an arrow. Sometimes you will see 0 V, and sometimes a 0. But this one here, we have to be very careful. This here, we have to be careful. Why? Because we may confuse, okay, confuse with the 0 element of R. So if there is no confusion, then we may drop the V. Otherwise, we have to be very careful. Usually, when I mention a 0, I will always put the vector 0, and therefore we're dealing with the 0 vector, not the number 0 from R. So now, so what is a vector space? So a vector space is a vector space is given by V plus and the multiplication by a number. So this it's a triplet. V is the set of vectors, the plus is the addition, and the dot is the multiplication by numbers. There is another here, another it's just something that people respect and take. We always, when we multiply a vector by a number, okay, here, remark, you will never see, so whenever you have alpha dot v vector, you never put the alpha to the right. I mean, okay, so we always put the scalar to the left and the vector to the right. Okay, I mean, sometimes you will see, like for example, I can divide a vector v. This is sometimes written, though we should write it this way, but sometimes we abuse it and we keep it this way. So this one is okay, though not advisable, but this one is out. Okay, so we always put numbers to the left, not to the right. So now we have a vector space. So let v plus dot. Okay, and again, if there is any confusion about the set of scalars, then we have to add it. In other words, we need to add either R or C for K. But in this case, as I said throughout this web note, I will always take the field to be the set of the real numbers R. So here there is something very interesting, is that if we take let v1, v2, vn, n vectors, and alpha 1, alpha 2, alpha n real numbers. So of course these are vectors. Then we can define alpha 1 v1 plus etc. alpha n vn. In other words, you can take vectors, multiply them by numbers, and you can add them. This is known, so this is v, and this belongs to capital V, where we used the multiplication and the addition of vectors, multiplication by scalar. So this here, in fact, has a name. It's called a linear combination vectors v1, vn. And this way, given a vectors v1, v2, vn, we can come up with an infinitely many vectors that are linear combinations by changing the constant alpha. In particular, the zero vector is a linear combination of the vectors v1, vn. It's enough to take all the numbers alpha equal to 0 to get the vector 0. Okay, so now notation. Okay, let us write the span of v1, vn to be the set of all linear combinations of v1, vn. In fact, we can extend this. Let A be a subset of V, A non-empty. So we have a set of vectors, and we can define the span of A to be the set of all linear combinations of vectors in A. Okay, so as we said earlier, obviously the zero vector 0 always belongs to span of A. So span of A is never empty, number one. And number two, okay, moreover, we have another property. Moreover, we have if V and W are in the span, so I have two vectors are linear combinations of vectors from A, then it's easy to see that alpha V plus beta W belongs to the span of A for any alpha beta in R. Okay, so in other words, linear combinations of linear combinations is also linear combination of the space. So these two properties, the fact that 0 is there and this property here, okay, defines what we call subspaces, the concept of subspaces. Okay, so here let W a subset of V. Okay, W is said to be a subspace of V if and only if 0 belongs to W and for any V W belongs to capital W and alpha beta in R, we have alpha V plus beta W belongs to capital W. Okay? So the structure of subspaces plays a major role in understanding vector spaces. So the concept of subspaces came from the study of linear combinations and the span. But in fact, we can prove, okay, beautiful result here, we can prove that any subspace W of V, okay, of V, we can prove that for any subspace W of V, there exists a subset of V such that W is the span of A. In other words, the subspaces are just the spans. But we have to be very careful because sometimes we have the span of a set of vectors, but most of the time when we're studying vector spaces and operations on vector spaces, etc., we may end up having a natural subspace, so not a set. We know that there exists a set A such that the span of A gives us W, but sometimes some of the subspaces are naturally defined, and that's why we need to separate between the two concepts. Do they coincide? Okay, good. In fact, we can also prove. Okay, we can also prove that there exists a subset of V such that W is the span of A and satisfies the following property. Okay, that for any V1 Vn in A and alpha 1 alpha 2 alpha n in R, okay, such that alpha 1 V1 plus alpha n Vn equal the zero vector, then alpha 1 equals alpha 2 equals alpha n equals 0. So in this case, this property here is known as the linear independence. So in this case, we say A is linearly independent. Set of vectors. So also A is called, in this case, A is also called an algebraic basis, a basis for W. So given a subspace W of V, there is always a basis. What's interesting is that if you have a basis, all the bases, there is not a unique base, and you don't have a unique set of vectors that will span a subspace. That's clear. So what happened is that what is unique is the number of elements of the set A, which is known as the dimension of W. So the dimension of W here, dimension of W is the number of elements of any basis. It's unique, it's independent of the basis, and therefore we call it dimension. So we have now two kinds of subspaces. We have subspaces with finite dimension, and we have subspaces with infinite dimension. So, of course, the concept of infinite dimension will exist if the space itself has an infinite dimension. So if the space does not have an infinite dimension, has only a finite dimension, then the concept of infinite dimensions subspaces will not, dimensional subspaces will not exist. So in any case, if a space has a finite, the entire space V has a finite dimension, then any subspace has a finite dimension. So example, if you take R, N, then we have finite dimension only, finite dimension only. All subspaces will have a finite dimension, and the dimension of Rn is n. Okay. If we take another example, okay, if you take the polynomial functions, sorry, if you take polynomial functions on R, okay, so this has an infinite dimension. Okay. Another concept that will be useful for us, especially when we're dealing with Hilbert space, is the concept of direct sum of subspaces. Okay, so let W1 and W2 be two subspaces of V. Okay, W1 and W2 form a direct sum of V if and only if, number one, W1 intersect W2 equal to the zero vector, and number two, for any V in capital V, there exist, and they are unique because of one, two vectors, W1 in W1 and W2 in capital W2, such that V is equal to W1 plus W2. Okay, so in this case notation, we will not say direct sum, we'll write that V is equal to W1 plus W2. Okay? Clearly, I mean, we can extend this. It doesn't have to be only two subspaces. We can have any number of subspaces and have the same definition. So keep in mind that the intersection between all of them, 2 by 2, of course, is due to the zero vector. They have nothing in common, and that any vector will be decomposed into a sum of vectors coming from these subspaces. So, for example, here, if we look at the case of, let's say, example, okay? So let's take R2, and let's take W1, the set of x0, x belongs to R, and W2, the set of 0y, y belongs to R. Okay, it's very easy to see, easy to show that R2 is equal to W1 plus W2. Okay, so this is a simple example of a direct sum of two subspaces in R2. More can be said about subspaces and their properties, etc., etc. But since we said it's just a little introduction, so let us move on. And the next one that is also useful is the concept of quotient spaces, quotient space, vector spaces. So let's V be a vector space, and W be a subspace of V. Okay, so let us define the relation between between vectors in V, if and only if v2 minus v1 belongs to w. So here, this relation R is an equivalence relation because W is a subspace, and therefore we have the for any vector or any v in V, we have the class of V to be the set of vectors W such that V minus W belongs to capital W. Okay? And it's very easy to see that, in fact, the class of V is the vector V plus W, where W is the entire subspace. Okay, so it's just a translation of the subspace W. Okay, and what's interesting is that if we take the set of all these classes, which will be denoted by V divided by W, or the quotient space, is the set of all these classes, okay, V in V, then this quotient space has a structure of a vector space, is a vector space. Okay, is a vector space. Keep in mind, okay, this is very important. This is a set of sets. So the class F, for every class, this is a set, not a vector. It's a set of vectors. So we have a natural definition. Okay, so it goes. Number one, what is the zero vector? The zero vector in V quotient W is the class of 0, which is 0 plus W, which is W. So W, the entire subspace in this quotient space, becomes a vector, the vector 0, the 0 vector. So it's really, you are taking the entire set and you are what? Collapsing it into a 0 vector. 2, the addition, okay, V1 plus V2, the class, sorry. So if you take two vectors and you want to define the addition of their classes, is the class of V1 plus V2. Again, we are using that W is a subspace. If W is not a subspace of V, this will not be a nice operation. You can define it, but it's not a nice operation. So here, and of course, third, alpha times the class of V is just the class of alpha V, and with these operations, the quotient space is a subspace. Finally, before we wrap up this introduction to vector spaces, let me just say, for example, to show you the beauty of this theory as a unifying theory of different areas. So, for example, let me just give some examples of vector spaces. Of course, we have Rn, okay, that's the natural one coming from R2. Another example, if you take, for example, continuous functions defined on an interval a, b into R, this has a structure of a vector space, and it's amazing because then functions are seen as vectors. 3, the one I mentioned earlier today, polynomials defined on R, okay, polynomial functions. Also, it is a vector space. 4, we can take, for example, Ri of AB, and these are functions which are Riemann integrable on AB. This also has a structure of a vector space. And then, of course, we can go to some complicated examples like little l2, little lp, c, c0. Just for the sake of c0 is the set of all sequences which goes to 0. C is the set of all convergent sequences. Little l2 and little lp will be defined in the special web note that I will consider on examples of normal vector spaces. Hope you enjoyed this web note, and good luck, and thank you very much.